The next bit is to do with the silicon chloride. So this is silicon tetrachloride. This is your AS period 3 chemistry. This is AS. Anything from AS can and will be asked in an A-level setting. So SiCl4 plus H2O, you get hydrolysis. So the type of reaction is hydrolysis, where you break the SiCl covalent bond and you get this white solid, which is the giant molecular structure of silicon 4 oxide, or what you call silicon dioxide, and you release these corrosive toxic fumes, and you have 4 chlorine, so you need 4 HCl, and since you have 4 HCl, you need to balance it with 2 H2O to get it up to 4 hydrogen, 2 oxygen, 2 oxygen for 1 mark. Okay, and what you will see is these you will see white fumes, and this is because the reaction is very exothermic. You only have to break 4 covalent bond here, and you are making a huge amount of covalent bond, because there are many covalent bonds. There are many strong covalent bonds in the giant molecular structure SiO2. So you are releasing a large amount of energy when you form a lot of covalent bonds here. And that makes the HCl come off as fume as a result of the large energy being released, and HCl has low boiling point, as you know it, due to its simple molecular structure. Of course, you also see this as a white solid, which it is insoluble in water, as you know from your periodicity, from your AS level knowledge. Okay, so next bit, draw a 3-dimensional diagram. You got to show the shape, you got to show the chloride. That is one thing, draw, and you have to give the bond angle. So I always like to label what I need to do in terms of how many points, and that's why there are 2 marks. This remind myself, have I done all the right thing? So I'll draw tetrahedral, 2 flat one, and then 1 coming out towards you. So these 2 are flat in the screen or on the paper itself. This is pointing at you, coming up from the screen, pointing at you right in the eye, and the other one is pointing away, behind the screen, away from you, behind the screen, behind the paper. Okay, and there's silicon and the bond angle. So the bond angle will be 109 degree. If you want, you can write 109.5. I typically learn tetrahedral as 109 degree, and I don't think that is necessarily a bad thing, because they do accept 109.5 degree. Okay, stick with one that you're happy with. So silicon react with oxygen to form a high melting point oxide. This was what I mentioned before, silicon dioxide, silicon 4 oxide, different names, same structure, same bonding, same formula. Okay, such as in terms of structure, where it has a high melting point, whereas the chloride has a low boiling point. So low boiling point means easily turn into a gas. Melting point means not very easy to go from solid to liquid, and there's 2 marks because there's point number 1 and there's point number 2. What is different between their structure? I talked earlier about silicon tetrachloride having a simple molecular structure. When we broke the 4 covalent bonds to hydrolyze it, and we form many strong covalent bonds between the silicon and oxygen in this giant molecular structure of SiO2. Okay, so SiO2 has a giant molecular structure. Okay, whereas SiCl4 has a simple molecular structure. So throughout my structure and bonding tutorial playlist, under the topical playlist, you'll see that I like to use the term giant molecular and simple molecular. Some textbooks or even your syllabus would have used giant covalent structure, simple covalent structure. They mean the same thing, and is to avoid confusing yourself, you should stick with one, but you should also know the other term as well. Like giant molecular is the same as giant covalent, so that when you see it, you're not confused, but you should stick with one in the explanation so that you're not alternating between the 2 every now and again. You should stick with whichever one you're comfortable with. All right, so what are we doing? Melting. Okay, so melting SiO2 requires a lot of energy to break many strong covalent bonds. So here for giant molecular structure, you need to break the strong covalent bonds between silicon and oxygen, whereas boiling, because they give us boiling point, so boiling SiCl4 only breaks weak van der Waals forces because you do not have permanent dipoles since SiCl4 is non-polar. As a result of four chlorine atoms, they are the same in this tetrahedral geometry, so the dipoles cancel out as a vector in that parallelogram. So I can't really pronounce that well. I remember once upon a time someone did make fun of me, and I still can't pronounce it very well. So it's a four-sided parallelogram. Okay, so you can think of dipoles cancelling out in that four-sided structure that I don't want to say again. Boiling SiCl4 breaks these weak van der Waals forces between the molecules. And because they're asking us to compare, I really must compare, okay? These require much lesser energy than to melt SiO2, okay? I'm pretty sure you have probably gotten the mark without comparing it because I talk about a large amount of energy and not a lot of energy. Well, actually I haven't talked about not a lot of energy, and this is about not a lot of energy to break these weak van der Waals between the molecules. Next bit, element A is in the same period, so this is period 3 chemistry. Again, is your AS level, period 3 chemistry, and this element reacts with dilute nitric acid. So what kind of element react with dilute nitric acid? We are thinking of metals or metal carbonates. However, this is element, so it's got to be the metals. They react with the acid to form a nitrate, a salt, and also hydrogen gas. The nitrate decomposes on heating to form an oxide. So we're looking at a group 2, MnO3 twice, all right? I've used M there to represent the group 2 metal, but they purposely give us A, so I can't use M really. I should use A instead of M, which is perfectly fine. You just change this to A, okay? So write an equation for the decomposition of the nitrate. So group 1 nitrate does not decompose easily, apart from lithium nitrate, which of course you know is the diagonal relationship, same as magnesium. So group 2 nitrate decompose easily, and lithium follows that trend because of the diagonal relationship. None of the other group 1 metals follow the same relationship as such. If I'm not mistaken, I think should be. Anyway, all I know is that the group 2 nitrate decomposition is a very common one based on your AS level group 2 chemistry. Okay, so ANO3 twice because it's A2 plus being a group 2 cation, and NO3 minus, this is your anion. So I hope you know you need one of these and you need two of these because the LCM, the lowest common multiple, to balance out the charges between 2 and 1, you need one of these, you need two of these because the lowest common multiple, LCM, is 2. So it will give you the group 2 oxide, A2 plus and O2 minus. It will give you 2NO2 because you got 2NO3, and it will give you O2 gas, which now you need to balance because you got 6 oxygen. You got 1 oxygen, you got 4 oxygen, 4 plus 1 is 5. I like to balance mine with a half. Some teachers and some students really hate fractions, and I don't know why. Okay, if you really don't like fractions, multiply the whole thing by 2, and you can get 1, you can get 4, you can get 2, you can get 2. To be honest, it doesn't matter. It's just a balance equation. As long as the molecular entities are maintained, as long as the number in front balance out the whole atoms on the left and right, it will be correct. So for that 2 marks, it's pretty generous there. So the oxide of element A has a high melting point. So we're looking at A being group 2 element. In fact, I don't think you use Roman numeral in A level because I'm getting confused between the O level where they use Roman numerals, and then in A level they use the Arabic numerals, and they go up to 18, and it's pretty bad of Cambridge, you know. Like there's no continuity at all. So you know group 2 is the same as this Roman numeral group 2. It doesn't matter, it's in the same period as silicon, so we're looking at group 2 and period 3, so that must be magnesium. So we're looking at magnesium oxide then. However, they're asking us what is the structure and also bonding present in it, in the oxide. Careful, in the oxide. So obviously we are looking at ionic bonding, and ionic bonding is present in giant ionic structure. Okay, and just like that you get the 1 mark, but you gotta specify structure as well as bonding. So what I've done really is I talk about the bonding first, and the structure does not matter. You can talk about this first and then that, as long as both are in the answer. So this next question is about transition metal chemistry. All right. They want you to use data from the data booklet to predict the geometry and the coordination number for sodium chloride. So they give you the cation radius over the anion radius ratio. So you really need the sodium and the chloride ionic radius, which you could get easily from the data booklet. That will give you 0.095 nanometer. That is 0.181 nanometer. So the RNA plus over the RCl minus is 0.525, and 0.525 is somewhere in between these. Okay, so the geometry of the cation will be octahedral, and therefore coordination number will be 6, because when you have octahedral, you can imagine the Na plus being surrounded by 16. Yeah. How about the Mg2 plus there? So the chloride doesn't change, but the Mg2 plus is 0.065 nanometer. As we know, the Mg2 plus is actually smaller than the Na plus. This is from your AS level periodicity. Your Mg2 plus cation radius over the chloride radius, we get 0.359. 0.359 falls into that category there. So that is tetrahedral. And you know, in a tetrahedral environment, you have 4 things bonded to you. So pretty straightforward there. So next bit is about the hydrolysis. So this is specifically the use of water to break the covalent bond, and you will get SiO2, and then you will get HCl. And this reaction is very exothermic. You will actually release quite a lot of heat. And well, balance equation, obviously, even though they don't ask you to balance any equation you write in A level, not just AS, in A level chemistry, in fact in O level also, you gotta balance your equation. Yeah. So they were very exothermic. They wouldn't necessarily just give you HCl dissolved in water. This will release the HCl, which also has a simple molecular structure. That's why it can boil off easily. It's just hydrogen chloride gas. So you can get white fumes. In fact, you get steamy white fume because it's very exothermic. Yeah? Are produced or are formed or seen. Okay, so yes, hydrogen chloride is a colorless gas, but because it's so exothermic, they can produce like fumes, right? So it's very easy to notice. You also get a white solid because the SiO2 is a solid forms. Okay, so this will come out as a solid. These are liquid and liquid. You will see solid forming. Okay, you want visual observations. Okay, so just stating the product is not going to help you. You need visual observations. So this is actually in your AS atmospheric chemistry. These are case study, and they are very, very important that you know what is going on here. The anode is acting as a catalyst because in the atmosphere, you do not have vanadium 5 oxide as your catalyst. So the SO2 go to SO3, and is it? Nope, sorry. I know what I want. I need to oxidize the NO to NO2 first. So that is plus O2 gas, give you NO2. Alright, so I need to balance that equation. So a lot of people will struggle if they just write the equation without balancing it. Okay, and then the NO2 is the one acting as the oxidizing agent to give you SO3. So the SO2 get oxidized to SO3. What happened to your NO2 then? Your NO2 get reduced because it's acting as an oxidizing agent. You see, this equation is balanced right away. The oxygen get transferred there. This is acting as oxidizing agent. You form more of this. How does this become back to NO2? The NO is acting as a catalyst, sorry. The NO is acting as a catalyst because you regenerate it at the end of the reaction. Okay? So how is it a catalyst? It is not used up by the reaction. Meaning to say, it is regenerated or reformed at the end of the reaction. the reaction being the oxidation of SO2 to SO3 in the atmosphere without the conditions that you require for contact process. Yeah. Describe with the aid of an equation the consequence of the oxidation of atmospheric sulfur dioxide. So you oxidize sulfur dioxide to sulfur trioxide in the atmosphere. So what happened then is the SO3 can dissolve in water. In this case, the water is not your industrial water, it's your rainwater. Then it will give you sulfuric acid that's balanced. That will give you your acid rain. So the acid rain form will corrode, I don't know, limestone building. What else? The dangers of acid rain, destroy crops, blah blah blah. Okay, so just a brief description really, because I've written my equation. I've shown that it can form acid rain. It's a balanced equation as well. That's the most important thing. And then just briefly describe the damages that it can do. So yeah, moving on to the first question. So this is about oxidative nitrogen. So this overlap with AS environmental chem. That is as part of nitrogen and sulfur chemistry under inorganic chemistry. So we know that we can get oxidative nitrogen when the nitrogen in the atmosphere undergo reactions when you get a lightning, because that is sufficient amount of energy to break apart the nitrogen-nitrogen triple bond and therefore allowing the nitrogen in the atmosphere, where you have about 78-79% of it, to undergo a reaction with the oxygen in the atmosphere. Yeah? And of course, the man-made action comes from the combustion of fuel, and that is high enough. There's high enough temperature in the car engine. Yeah? In the car engine, for the nitrogen that's present in the atmosphere to be broken, the nitrogen triple bond to be broken, and therefore to undergo reactions. All right.